Amazon Redshift. Introduction to Amazon Redshift and Amazon Redshift Serverless. 1. Fully managed data warehouse. Amazon Redshift takes care of management tasks so you don't have to. 2. Petabyte scale, capable of handling vast amounts of data up to petabytes. 3. Amazon Redshift Serverless, allows querying without the need for pre-configuring a data warehouse. 4. Auto-provisioned resources, resources are automatically set up for you. 5. Intelligent scaling, Redshift adapts to deliver fast performance for various workloads. 6. Cost efficiency, you're billed only for what you actually use. 7. Query Editor v2, you can start querying immediately using Amazon Redshift's Query Editor version 2. 8. By tool compatibility, compatible with most business intelligence tools. 9. SQL features, offers familiar SQL functionalities for data querying. 10. Zero administration, an easy-to-use environment that requires no admin work. Amazon Redshift is a managed data warehouse service that offers an efficient, scalable, and secure platform to manage and analyze vast datasets. Data types, Redshift can handle various types of data including transactional, data related to transactions like purchases. Clickstream, data collected from web pages about user activity. IoT telemetry, data from IoT devices, sensors, and applications. Application logs, log data generated by various applications. Features, key features of Redshift include serverless, no server management required, automatically scales. Elastic scaling, scale storage and compute resources according to needs. Zero ETL integrations, directly connect with various data sources without ETL processes. Benefits, with Amazon Redshift, users benefit from real-time analytics, immediate insights from vast data sets. Data-driven applications, develop apps based on data-driven decisions. Advanced security, ensures top-notch security, governance, and compliance. Insights, Redshift allows users to analyze, deep dive into datasets for specific queries. Visualize, create graphical representations of data patterns. Predictive analytics, forecast future trends based on historical data. Features of Amazon Redshift, Part 1. 1. Snapshots, allows restoration from Amazon Redshift serverless snapshots. Useful for data recovery. 2. Recovery points, automatic creation every 30 minutes, kept for 24 hours. Useful for restoring after accidental data loss. Snapshots can also be created from recovery points. 3. Base RPU capacity, control the balance between resources and cost. Default is 128 RPUs, with a single RPU providing 16 GB of memory. It impacts query performance and cost. 4. Usage limits of data sharing, limit data transfer between producer and consumer regions. Data transfer costs differ by AWS region, measured in terabytes. 5. User-defined functions, UDFs, enables the running of UDFs in Amazon Redshift serverless. Features of Amazon Redshift, Part 2. 1. Stored procedures, execute stored procedures in Amazon Redshift serverless. 2. Materialized views, allows creation within Amazon Redshift serverless. 3. Spatial functions, execute spatial functions in the platform. 4. Federated queries, join data with Aurora and Amazon RDS databases from within Amazon Redshift serverless. 5. Data lake queries, execute queries joining data from Amazon S3 data lake with Amazon Redshift serverless. Features of Amazon Redshift, Part 3. 1. Hyperlog log functions, utilize hyperlog log functions in Amazon Redshift serverless. 2. Querying across databases, access data across multiple databases with Amazon Redshift serverless. 3. Data sharing, access data shares on provisioned data warehouses. 4. Semi-structured data querying, ingest and store with the superdata type. 5. Tagging resources, use AWS CLI or the Amazon Redshift serverless API for tagging resources with metadata. Features of Amazon Redshift, Part 4. 1. Machine learning, integrate Amazon Redshift machine learning with Amazon Redshift serverless. 2. SQL commands and functions, use Amazon Redshift SQL commands and functions, with few exceptions. 3. CloudFormation resources, deploy and update Amazon Redshift serverless resources using CloudFormation templates. 4. CloudTrail resources, integrated with AWS CloudTrail to record actions. Captures all API calls as events. 1. Integration with various applications. Amazon Redshift supports multiple data loading, ETL tools, and BI tools due to its basis on open standard PostgreSQL. Most SQL clients require minimal changes to integrate. 2. Core component, clusters. The fundamental infrastructure of Amazon Redshift is a cluster, which consists of compute nodes. For 2 or more compute nodes, a leader node is present for coordination. 3. Role of the leader node. The leader node manages communication, parses SQL statements, creates execution plans, compiles code, and sends it to compute nodes. 4. Compute nodes functionality. Compute nodes execute the compiled code from the leader node, sending intermediate results back for final aggregation. They have dedicated CPU and memory, which can be scaled up. 5. Redshift Managed Storage, RMS. This is where data is stored, allowing scaling up to petabytes using Amazon S3. It provides flexibility in scaling compute and storage separately and uses optimizations for enhanced performance. 6. Concept of node slices. Compute nodes are divided into slices, each processing a part of the workload. Data distribution to slices is managed by the leader node. 7. Internal network features. Amazon Redshift uses high bandwidth connections for fast communication between the leader and compute nodes. Compute nodes are on a separate, inaccessible network for client applications. 8. Amazon Redshift databases. A cluster can contain multiple databases, with user data on compute nodes. The SQL client communicates primarily with the leader node. 9. RDBMS compatibility. Amazon Redshift functions as an RDBMS and is thus compatible with other such applications. While offering regular RDBMS functions, it's optimized for analyzing large datasets. Performance of Amazon Redshift. 1. Massively parallel processing, MPP. Redshift employs MPP to run complex queries on large datasets swiftly. Each compute node's core runs the same query segments on different data parts. This parallelism allows faster data processing and query execution. 2. Columnar data storage. Utilizing columnar storage for tables decreases disk I/O needs. This method reduces data loading from disk, promoting efficient in-memory query processing. Proper column sorting further enhances filtering. 3. Data compression. Reducing storage via compression enhances query performance. Compressed data, when queried, is decompressed during the execution. As similar data is stored together in columnar storage, adaptive compression encoding is applied, making data analysis efficient. 4. Query optimizer. Redshift's query engine features an MPP-aware optimizer optimized for columnar data storage. This optimizer is designed for intricate analytic queries with multi-table joins, subqueries, and aggregation. 5. Result caching. For faster query results and better performance, Amazon Redshift caches specific query results in the leader node's memory. When similar queries are submitted, cached results are used, bypassing the need for a rerun. 6. Compiled code. Optimized compiled code is spread across the cluster's nodes. This compilation reduces interpreter overhead, making complex query runs quicker. Cached compiled code is also shared across sessions, ensuring faster subsequent query runs. In a typical relational database with row-wise storage, each data block stores values for consecutive columns for a single row or a small number of rows. This approach is ideal for OLTP databases, where the focus is on quickly reading or writing entire records. Columnar storage, as employed by Amazon Redshift, is different. It stores values for a single column across multiple rows in each data block. This leads to a reduction in I/O operations, as each data block can hold values for up to 3 times as many records compared to row-based storage. This efficiency increases for tables with a large number of columns and rows. Additionally, columnar storage allows for data type-specific compression, reducing both disk space usage and I/O operations even further. Workload management in Amazon Redshift. 1. Prioritizing workloads. Amazon Redshift's workload management, WLM, helps manage query priorities, ensuring short queries don't wait behind long ones. 2. Query queues and service classes. WLM dynamically creates query queues based on service classes, including both internal system and user-accessible queues. The term queue is used for both user-accessible service classes and runtime queues. 3. Query assignments. When a query is run, WLM determines its queue based on the user's group or by matching a query group in the queue configuration to a runtime set query group label. 4. Default setting, automatic WLM. By default, clusters using the default parameter group apply automatic WLM, which oversees query concurrency and memory allocation. 5. Manual WLM features. In manual WLM, Amazon Redshift sets up one queue with a concurrency of 5 and a superuser queue with a concurrency of 1. Users can create up to 8 queues, each with a max concurrency of 50. The total concurrency for all user-defined queues, excluding the superuser queue, caps at 50. Amazon Redshift, Table Design Best Practices Part 1. 1. Choosing the best sort key. To optimize your table for queries, it's vital to select the most appropriate sort key. 2. Auto sort order. Allow Amazon Redshift to select the sort order by specifying auto for the sort key. 3. Timestamp as leading column. If recent data is frequently queried, set the timestamp column as the leading column in the sort key. 4. Efficient queries with time range. This aids in skipping entire blocks that don't fit within the queried time range. 5. Column specification for range/equality filtering. If a specific column is frequently range filtered or equality filtered, use it as the sort key. 6. Joining tables, sort and distribution keys. For tables that are often joined, specify the join column as both the sort key and distribution key. 7. Sort merge join benefits. This facilitates the query optimizer to select a sort merge join, which is more efficient than a hash join, bypassing the sort phase. Amazon Redshift, Table Design Best Practices Part 2. 1. Distribution style selection. How data is distributed impacts query performance significantly. 2. Fact table and dimension table distribution. Distribute them based on their common columns. 3. 1 distribution key limitation. A fact table can only have one distribution key. 4. Dimension selection criteria. Choose one dimension to collocate based on join frequency and the size of joining rows. 5. Cardinality and filtered result. Consider distributing tables on columns with high cardinality in the filtered dataset. 6. All distribution consideration. For certain dimension tables, distributing the entire table to all nodes using all distribution might enhance query performance. However, consider the implications on storage and load times. Amazon Redshift, compression encodings. 1. Let copy command decide. In many cases, allowing the copy command to choose compression encodings offers optimal results. 2. Encode auto default. By default, Amazon Redshift manages compression for all columns in a table with encode auto. 3. Copy commands role. This command analyzes data and applies compression encodings automatically during the loading phase. 4. Balancing with automatic compression. Ensures that sort key columns remain balanced with other columns in a query. 5. Scenario, sort key and varchar columns. There might be better performance options for specific table configurations, such as when the sort key is a date and there are large varchar columns. 6. Performance cost consideration. Only empty tables without prior compression encoding experience this performance cost. Amazon Redshift, key constraints and column size. 1. Primary and foreign key constraints. Define them between tables to help the query optimizer generate efficient plans. 2. Amazon Redshift's constraints handling. These constraints are informational. Amazon Redshift does not enforce unique, primary key, and foreign key constraints. 3. Column size importance. Avoid using the maximum size. Instead, size columns based on the largest anticipated values. 4. Date/time data types efficiency. Date and timestamp data types provide more efficient storage and better query performance compared to char or varchar when storing date/time information. On Redshift, data loading best practices. 1. Use the copy command. Efficiently loads data from various sources like Amazon S3, EMR, DynamoDB, or remote hosts, more efficient than insert statements. 2. Prefer single copy command for multiple files. Amazon Redshift can parallelly load from several compressed files. Using multiple concurrent copy commands can lead to slower serialized loads. 3. Understand data file formats. Files come in various formats and compression. Loading from files that can be split allows Redshift to use its MPP architecture, dividing the task among nodes. 4. Compress data files. It's recommended to compress large load files using zip, LZOP, zip2, or standard. Then specify the chosen method in the copy command. 5. Verify data files pre and post load. Before loading, ensure the correct files are in the Amazon S3 bucket. After loading, query the stl_load_commit system table for verification. 6. Opt for multi-row and bulk inserts. If copy isn't an option, use multi-row inserts for efficient data compression and bulk insert with a select clause for better performance. 7. Maintain data in sort key order. This avoids the need for a vacuum. If data follows the existing rows properly, there's no need to vacuum. 8. Load data sequentially. If adding large amounts of data, load them in order according to the sort key to negate vacuum needs. 9. Implement time series tables. Organize data with a fixed retention period as a sequence of time series tables. This allows for easier data management. 10. Schedule around maintenance windows. If maintenance occurs during a query, it might be terminated. It's best to schedule data operations to avoid these windows. Amazon Redshift Query Design Best Practices, Part 1. 1. Design tables for optimal query performance. Ensure you follow Amazon Redshift's guidelines for designing tables to enhance query performance. 2. Avoid using select. Instead, specify the columns you need, which reduces data transfer and speeds up queries. 3. Use case for complex aggregations. Utilize case conditional expressions for intricate aggregations to avoid selecting from the same table numerous times. 4. Limit cross joins. Only use them when essential, as they can be computationally expensive and slow due to the resultant Cartesian products. 5. Use subqueries effectively, especially when a table in the query is just for predicate conditions and the subquery returns a limited number of rows, for example, under 200. 6. Use predicates to restrict datasets. This helps in enhancing the query performance by limiting the amount of data to be processed. 7. Prioritize comparison condition operators. These are more efficient than like operators, which are still more preferable than similar to or POSIX operators. 8. Minimize function use in predicates. Functions in query predicates can increase the query's cost, thus affecting performance. Amazon Redshift Query Design Best Practices, Part 2. 1. Utilize where clause effectively. It helps restrict the dataset and aids the query planner to use row order, reducing the scanning of unnecessary disk blocks. 2. Add redundant filters in joins. Even if filters apply the same, it aids Amazon Redshift to filter before the scan step, increasing efficiency. 3. Sort keys and group by clause. Helps the query planner use more efficient aggregation. One-phase aggregation is possible when group by contains only sort key columns, including the distribution key. 4. Match group by and order by columns. Ensure columns are in the same order in both clauses to avoid mismatches and potential query inefficiencies. Amazon Redshift Copy Command. 1. Copy command, a method to load data from Amazon S3 into Amazon Redshift. 2. Parallel processing, uses Amazon Redshift's massively parallel processing, MPP, architecture for faster data loading from multiple files in an S3 bucket. 3. Source data formats. Data files can vary in formats and compression algorithms. The copy command loads all files referenced by the S3 bucket prefix. Parallel versus serialized data loading. 1. Parallel loading. Amazon Redshift leverages its MPP architecture to load data from multiple files or split files in parallel. This distributes the workload among different nodes in the cluster. 2. Serialized loading occurs when data is loaded from a file that cannot be split. This method is considerably slower compared to parallel loading. Loading split data files. 1. Splitable file types. Examples include uncompressed CSV, CSV compressed with bzip, and columnar files like Parquet/ORC. 2. Automatic split criteria. Amazon Redshift automatically splits files of 128 megabytes or larger. Columnar files, such as Parquet and ORC, aren't split if they're below 128 megabytes. 3. Parallel loading. Redshift uses slices working in parallel for fast load performance. Loading non-split data files. 1. Non-split file types. Files like JSON or CSV compressed with algorithms like zip aren't automatically split. 2. Manual splitting. It's recommended to manually split these files into smaller sizes, ideally from 1 megabyte to 1 gigabyte after compression, and ensure the number of files is a multiple of the cluster slices. 3. Distribution keys. Utilize parallel processing by setting distribution keys on tables. Data loading mechanism. 1. Data load target. Data gets loaded into the target table, with one line per row. 2. Matching fields. Fields from data files match the table columns in sequence, left to right. Fields can be fixed width or character delimited, with a pipe, vertical bar, being the default delimiter. 3. Default values. If a table column isn't specified in the copy command's column list, it's loaded with its default value. Amazon Redshift Spectrum Overview. 1. Dedicated servers. Amazon Redshift Spectrum operates on dedicated servers separate from your cluster. 2. Compute-intensive tasks. It offloads tasks like filtering and aggregation, utilizing less of the cluster's capacity. 3. Scales intelligently. Depending on query demands, it can use thousands of instances, leveraging massively parallel processing. 4. Table creation. Spectrum tables are created by defining file structures and registering them in an external data catalog. 5. External data catalogs. These can be AWS Glue, Amazon Athena's catalog, or your Apache Hive Metastore. Any changes are instantly available across your Redshift clusters. 6. Partitioning benefits. Partitioning external tables can enhance performance by allowing the query optimizer to ignore irrelevant partitions. 7. Querying Spectrum tables. Once defined, you can query and join Spectrum tables like standard Redshift tables, though updates aren't supported. Any Redshift cluster in the same AWS region can query updated S3 data files instantly. Distribution styles in Amazon Redshift. 1. Auto distribution. Amazon Redshift assigns an optimal distribution style based on table size. It can change from all to key or even as the table grows. View actions using SVL_auto_worker_action and recommendations with SVV_alter_table_recommendations. Default distribution if not specified. 2. Even distribution. Rows are distributed in a round-robin manner. Suitable when a table doesn't join or when there's no clear choice between key or all distribution. 3. Key distribution. Rows are based on the values in a column. The leader node places matching values on the same node slice. This collocates rows on the slices according to values in joining columns. 4. All distribution. A copy of the whole table is distributed to every node. This ensures every row is collocated for every join. Requires more storage and is suitable only for slower moving tables. Effects and recommendations for distribution styles. 1. Auto distribution impact. Changes occur in the background, with minimal user query impact. Initially, it may be set to all for small tables, later changing to key or even as data size increases. 2. Viewing distribution styles. To view applied distribution styles, query the PG_class_info system catalog. If not specified with the create table statement, auto distribution is applied. 3. All distribution storage impact. Storage multiplies by the number of nodes, leading to longer load, update, or insert times for multiple tables. Best for tables not frequently updated. 4. Distribution redefinition. You can sometimes change a table's distribution style after creation. When not possible, recreate the table and use a deep copy. Important notes on Amazon Redshift distribution. 1. Amazon Redshift cluster level handling. After specifying a distribution style, Amazon Redshift manages data distribution at the cluster level. 2. No partitioning required. There's no need for partitioning within database objects. Table spaces or partitioning schemes for tables aren't needed. 3. Changing distribution styles. In some scenarios, distribution style can be changed after table creation. When not possible, the table must be recreated and populated with a deep copy. Performing a deep copy. 1. Deep copy overview. A deep copy is a method to recreate and repopulate a table using specific techniques. 2. Bulk insert benefit. Bulk inserts in a deep copy can automatically sort a table, making it a faster option compared to a vacuum, especially for tables with a large unsorted region. 3. Recommendation for concurrent updates. It's suggested to only execute concurrent updates during a deep copy if they can be tracked. After the deep copy is done, any delta updates should be moved to the new table. Concurrent updates are supported automatically by a vacuum operation. Methods to create a copy of a table. 1. Use original table DDL. If the create table DDL is available, it's the fastest and most recommended method. All table and column attributes can be specified, and the original DDL can be located using the show table function. 2. Use create table like. This method is suitable if the original DDL isn't accessible. The new table will inherit attributes like encoding, distribution key, sort key, and not null attributes from the parent table. However, primary and foreign key attributes won't be inherited but can be added using alter table. 3. Temporary table creation. To maintain the primary and foreign key attributes of the parent table, especially if there are dependencies, you can use create table, as, CTAS, to create a temporary table. After, you can truncate the original table and repopulate it from the temporary table. This method offers improved performance compared to permanent tables but comes with a risk of data loss. Creating materialized views in Amazon Redshift. 1. Need for complex queries. In data warehouse environments, applications often execute complex queries on vast tables, such as multi-table joins and aggregations on tables with billions of rows. These queries are resource-intensive and time-consuming. 2. What are materialized views? Materialized views in Amazon Redshift contain pre-computed result sets derived from an SQL query over one or more base tables. They enable querying just like other database tables or views. 3. Benefits of materialized views. When querying a materialized view, Amazon Redshift returns the pre-computed results without accessing the base tables. This results in significantly faster query response times compared to querying the base tables directly. Thanks for watching.